We're looking good. Coming up on entry. Vehicle reports entry interface. We are beginning to feel the atmosphere as we go in here. It is reporting that we are seeing G's on the order of 11 to 12 Earth G's. Commercial 2 is starting. We are now getting telemetry from Odyssey. We should have parachute deploy around Mach 1.7. The parachute is deployed. We are decelerating. Heat shield has separated where we found the ground. We're down to 90 meters per second at an altitude of 6.5 kilometers descending. Standing by for back shell separation. We are in powered flight. We're at altitude of 1 kilometer descending. Standing by for sky crane. Sky crane is started.
Signal to Odyssey, remain strong.
Touchdown confirmed. We're safe on Mars.
Got thumbnails.
Welcome to NASA's Jet Propulsion Laboratory in Pasadena, California. And I think that video just brought a few tears to a few of the eyes up here on the podium. Let me introduce the panelists that we have today that are going to give us an update on the rover and a little bit of the outlook for what will come next. Joining us right now we have Michael Watkins from JPL. He's the mission manager for the Mars Science Laboratory. Miguel San Martin from JPL, the chief engineer of guidance and control. Sarah Milkovich from JPL. She's the high-rise investigation scientist. And John Grotzinger of Caltech, the project scientist for the mission. And we'll begin with Mike Watkins.
Okay, good morning, everyone. Welcome to Mars, or welcome back to Mars if you were here last night. The surface mission of Curiosity has now begun. Now, for a long time, those of us on the project knew that we had to get through some big events. Launch was a big one for us, and of course, EDL was an enormous one for us. But we built this rover not just to be launched or not just to land on Mars, but to actually drive on Mars and execute a very complex and beautiful science mission. We have ended one phase of the mission, much to our enjoyment and to the joy of a lot of folks here in the audience and on our own team. But another part has just begun. And really, it's really the fundamental reason we built the rover. It's really the purpose of the rover. We're just starting that mission. We're not ending it. Now, about 2 hours after landing, just before 1 a.m. in the morning, Curiosity called us via the next overpass of Mars Odyssey. So Mars Odyssey was overhead during EDL, and of course, it comes around 2 hours later. Mars has rotated a little bit. And was still over the horizon, and we were able to have a short talk with Curiosity via Mars Odyssey. And she told us that she is in surface nominal mode. She correctly transitioned from EDL mode to surface nominal, not in safe mode, in regular nominal operational mode, and is otherwise very healthy. We had a very successful UHF pass. We got some images that I'll show in a little bit, and we are go for all planned Sol-1 activities. Now, the Sol-1 activities are really dominated by, in some sense, kind of boring activities. Checking out the rover, making sure it's healthy, deploying the antenna. On Sol 2, we deploy the remote sensing mast. So the high gain antenna, the rover looks kind of like this right now. Now you're used to seeing the rover like it is in that picture, with its eyes up and with an antenna deployed. In fact, we are stowed down here with the remote sensing mast down, and we're about to deploy this little antenna here. This allows us to talk directly to the Earth with enough gain that it can actually send data to us and be more easily talked to by us. Later, a day or so from now, we're then going to deploy the remote sensing mast so we can take these beautiful panoramas that we've all been waiting to see. But as for now, the first order of business is make sure that our communications to the Earth are healthy, and that's the prime activity for upcoming for today. But last night we got one other beautiful piece of information, and that is a HazCam image. Now, our HazCams, we saw them last night during EDL. These are little cameras that point mostly at our wheels and at the ground in front of us, in the front and the back. And when we land, we're concerned that we're going to kick up some dust, right? We're firing rockets, and we might be throwing up a plume of dust. And so we have little clear covers on them. And those are the images that we got last night at landing, the very first things that we were clapping about in the control room. So if we could show the first graphic, this is that picture. So now that we're all, awake and we've digested this and we have a little bit less adrenaline, that it's not such a great picture anymore, right? Right? It's beautiful. It's beautiful to us, right? It's beautiful to us because of what it means. But you can see there's a lot of stuff on the lens there, and that is actually dust kicked up by the landing event. So we want to get rid of those covers. You can see our beautiful shadow there, and we love that. We hoped to get the rear and the front down. This is a front HazCam with the sun's behind us, and you can see our shadow there. But let's go to the next. Let's go to the animation and remind you where these HazCams are and what you're about to see in the next image and the cover deploy, right? So they're looking for mobility hazards, right? That's what we call them, the HazCams. So there they are, kind of pointed at the ground. They have a wide field of view, kind of a fisheye type lens. Okay, that's the cover deploy, right? And there are the cameras. So let's go to the next image. So last night, after landing, we fired all of our pyros, released these covers, took these HazCam images, and these are the things that came down just before 1 a.m., right, here on the West Coast. Okay, so there is our image, and we're looking out the back. You can see the left rear wheel there. You can see a little bit of that hinge actually in the field of view there. You see the kind of looks like a spring there on the lower right side of the image. And then on the upper left is part of the RTG, right? The power source. That's one of the radiator fins that we're seeing there on the side. And several of the folks that worked on assembling the rover in Atlo and test said they never got a picture this good. They could never get the lighting quite right here on the Earth. And so this is the definitive control image now of how the rover is supposed to look here on Mars. And over on the side there, you're going to see over on the right side, you see some hills there. Over on the far edge there, and John Grotzer is going to show that later. Now, I personally have to say I really love these images because later we're going to get magnificent color panoramas and 3D images and magnificent things on Mars. But these first images somehow are always the best ones to me because when you land on Mars, it's new every time. And this is a new place on Mars. We go on vacation to see a different part of the Earth. It's on our own planet. And here we're seeing a part of Mars we've never seen before. And later you'll see a kind of a zoom in of this part of Gale Crater's rim here in kind of reoriented so it looks more like a landscape that we would recognize on the Earth. But we're going to continue to get the front version of this one with the shadow that we had yesterday out that same direction. We'll be coming down later today. And then over the next couple of days, we'll be sending down the hand lens imager, which is in color. And after we get the RSM up, we will get some nice black and white panoramas first. Now, this is our new home, at least for a while, here on Gale, and we need to explore it and take a look around, and then, of course, eventually head for the hills. Now, we actually hope in the front HazCam that should be coming down in a few hours from here, we can actually see the mountain of Gale. We think we're pointed kind of east-southeast, about 112 degrees heading. We're at a very slight tilt. We are, in fact, let me look at it here. We are 3.6 degrees negative in pitch, so the front is down by about 3 degrees, and we are left side down about 2 degrees. Now, those are pretty small numbers. We landed pretty much on this table right here. It's pretty flat. We're in a pretty good spot here. But there's still the question, where exactly is this spot on our maps of Mars? And to talk a little bit about that, we have Miguel San Martin.
Thank you, Mike. So, good morning. I hope you enjoyed the roller coaster ride last night. I sure did. Actually, I want to get another round, and maybe they have to wait a few more years. And so, the EDL looked beautiful from our monitors. Of course, we haven't had the time to look the data carefully, and the data is going to be coming soon. I mean, right now the rover is full of EDL, a treasure trove of EDL data that is going to help us, once we download it, understand and bring our knowledge of EDL to even higher levels, which is, we are very excited right now, the EDL team, waiting for that data. So I'm going to talk to you about our best knowledge right now of where we landed. Okay, it's not, that might change when we get high-rise data, but this is what we know the best at this point. So next picture. Okay, well, we did land inside the crater, so we know that. And you can see there our landing ellipse, 20 kilometers by 7 kilometers. And so if we can get the next picture, please. And there's the dot of where we think we landed. This is 2 kilometers east of the landing, of the center of the landing site, of the aim point, and about, I believe it's a few hundred meters north. Now, let me explain to you where we get that estimate from, okay? This estimate is based on ground navigation done here on the ground by the navigation team that Thomas Martin Moore leads, that, as you saw yesterday, gave us tremendous, incredible precision in navigation, that we seeded the navigation software of Curiosity with that very precise data. And then Curiosity using its own navigation instruments, in particular what we call an inertial measurement unit, which is it's a relative instrument that can take an initial seed of what the position and velocity is, and it can propagate forward as it measures all the forces being applied to the spacecraft by the atmosphere and its own rockets. So it can, but it is kind of a dead reckoning. So it's kind of like the odometer in a car counting wheels. Okay, so it tends to accumulate error. Okay, so but that's, so in essence, that point is based on one of the last EVRs, the last piece of telemetry that the spacecraft told us when it touched down. Says, I touched down, and this is where we are. Very confident the spacecraft tells you that. And then, obviously, we need to analyze it, and that's the point, with some corrections that we did with our friends at Langley, based on some technicalities that probably we shouldn't get into. But we actually get other indications from the data that we saw in the telemetry that gives us the impression that we actually did very well. Like, for example, one sanity check that we do is that eventually, after propagating with the inertial measurement unit for several minutes, for 4 minutes, eventually we remove the heat shield, and the radar starts looking at the ground. And now we can see how well, in some aspects, the inertial measurement unit did, and how well Thomas did, okay, because it gives us altitude and velocity relative to the ground. And actually, they agree tremendously well. It's within, I mean, it's just so well that we have to look at the data again because it's hard to believe. We haven't been able to get our simulations to work that well, and I'm seriously, yeah, it was a correction of a few meters in altitude and in velocity less than a meter per second, okay? And by the way, and that is also influenced by how well we did, how good was our last attitude fix based on the stars, okay? Just like the old sailors did, we still use the stars, and I think that's great. I mean, it connects us with the past. So we did the final looks at the stars. We figured out that Curiosity did that all on itself, looked at the stars, took the navigation data from the ground, and then it took it all the way down and guided the spacecraft. And that's the best knowledge of where we are. We think that within a kilometer is our estimate, but we have to wait for precise localization by high-rise. So that's all I have to say. Thank you. Sarah?
So speaking of high-rise, we heard a lot. You've heard a lot about how Odyssey was listening to MSL as it came in for landing, but Odyssey wasn't the only orbiter there listening. Mars Reconnaissance Orbiter was also there, and MRO wasn't just listening, we were watching. So the high-rise camera is one of the cameras on MRO, and we normally take pictures of the surface, and we can get pictures up to resolutions of 30 centimeters per pixel, which is just really fantastic. But what we did this time, if you can go to the graphic, there's MRO coming along, and we actually took a picture with high-rise as MSL came in on the parachute. So you can see the little dot there is MSL moving across. The box shows our image. There's the parachute. And if we zoom in, there we go. And this is really a testament to the high-rise team, Alfred McEwen, the principal investigator, and the high-rise operations team at University of Arizona, and the MRO spacecraft team. This was really, we've been working on putting this imaging sequence together since about March. We've been tweaking it and updating it as MSL has been getting closer and closer to Mars, but the final commands were sent up a couple days ago. And this image was taken 6 minutes after MSL entered the atmosphere, and MRO was about 340 kilometers away from MSL at the time the picture was taken. You can see the lines on the parachute. You can see the hole in the top there. That inset image is been stretched differently so that you can see the parachute clearly without saturation. And let's see if we go. I think that's the last one, or we can go to the last one. So yes. So this is, we have taken, high-rise has taken over 120 pictures of Gale as part of the landing site selection and characterization process, but I really think this is the coolest one. So now John is going to talk about what we see on the surface.
All right, thanks, Sarah. Okay, so let's just go to the first graphic right away, please, and get you back into the HazCams. Tell you a little bit about that. Here's an image, our sort of standard color, Viking era color superimposed on top of a CTX DEM and showing the topography of Gale Crater. You can see the well-defined crater rim there, the landing ellipse, and Mount Sharp towards the middle. And to help you understand what we're going to be seeing in the HazCams, let's just get oriented a little bit. So north is up here towards the top of the image, and therefore if you go counterclockwise, that takes you into the northwest quadrant, and there you see the rim. So the northern rim of Gale Crater is actually considerably lower in elevation than the summit of Mount Sharp, and you can even see where the rim is breached a little bit there. But remember the topography. Remember the topography of the rim. You're going to have to keep that in mind. And then Mount Sharp itself is also going to represent a topographic rise. And as Mike mentioned before, the spacecraft is oriented northwest-southeast, pointing forward towards Mount Sharp. And so if we go to the next image, this is really spectacular. What's happened here is Justin Mackey and Bob Dean worked to take the HazCam image. Remember, this camera has a fisheye lens, so there's a lot of distortion due to the extreme curvature of the lens. And by restoring that, you go back to the horizontal here. So this would be the view that you would see if you were a HazCam on the surface of Mars. And there we are looking rear HazCam towards the rim of Gale Crater. And this couldn't have been a better position to land in because we get to see rearwards and forwards. And in this view, you see the rim of the Gale Crater. You've heard us speaking about the alluvial fan that we think we've landed very close to the end of. And this is the source area. So this is bringing materials in from the rim, which is not our destination. But we're getting a free sample without having to drive over there potentially if we're able to drive the rover and discover the right kind of geology that really could represent the distal part of this alluvial fan. And in the foreground, you see a scene that's very familiar to you from other images of Mars, what is undoubtedly a windswept plain with coarse fragments left behind. The science team is initially impressed by the rather uniform grain size distribution of the coarser particles. We don't yet know what that diameter is, but you can get the sense qualitatively that there's a bunch of particles there that are about the same size. So in the upcoming sols, we're going to be debating this and discussing it and trying to figure out where to go and what to do, but this will be part of the story. A target like this is interesting scientifically because one of the things that we're going to want to do after the commissioning period is over is scoop up some of the soil and analyze it. And what we would really like to do is analyze something that we feel is very representative of Mars. So something like this is potentially a target for us to think about, and by sampling it and measuring it, we then have a sample of what could be the most global sample of Mars that we could measure. Okay, now in the next one, this one's tough. Okay, this one, I think the EDL guys were probably seeing a vision like this a few hours ago. But what you can see now, again, remember the curvature is taken out. We are looking towards the southeast. You've got the shadow of the rover there, and this was the first indication that we were looking southeast because the sun was setting behind us. And gosh, I just realized I forgot to point something up. This is important. Is it possible to go backwards? Two, please, to the first one.
Stand by. That one or one earlier?
One more, please. There we go. Okay, so look at the landing ellipse. If you go to the southwest part, notice that black line that goes from northeast to southwest through that. That's this dune field, which lies at the base of Mount Sharp there. This is beautiful in all the high-rise images that have been collected. And so that black line is going to be our frame of reference. And as Miguel showed, we have landed somewhere to the north of that black line in the ellipse, and in the HazCam image, we're looking towards the base of Mount Sharp. So now let's advance 2 again. There we are, right on the money. That black line, about 3/4 of the way up there, we believe, is the dune field, that black line of dunes. And therefore, as you work upwards in the image, very fuzzy in there, we believe you see the outline of Mount Sharp itself, bright in the setting sun. And the upper part then is the horizon in the sky, which would look darker. So you should see a slope which goes from above that black line of dunes, sloping to the upper right and separating light below from dark above. And we believe that's the silhouette of Mount Sharp in the setting sun. So you have a little bit of adventure before you. I'll be sleeping when the next downlink occurs, and Joy Crisp will be able to talk to you about the data that we'll get down that will be without the dust cover and higher resolution, possibly even full frame to confirm this. But we think we've landed, and the HazCams are picking up the topography on opposing sides of our landing ellipse. So that's it for me.
That means we'll open it up to questions now, and we'll get a microphone to you, and I am going to try to memorize the order in which I see hands come up, and we'll start over here on this side and work our way over. Thank you.
Kelly Beatty, Sky and Telescope. Mike, could you refine the landing time as best you know it for us? I was a little confused by a timestamp in Miguel's image which said 22:38:50. So what was the landing time as best you know?
I will actually have to get that to you after this press conference. I don't. No. So, well, we'll get it. We'll get it for you. Yeah. Rob, do you know? All right, we'll get it to you just after. Excuse
me, Scott Gold at the Los Angeles Times. Can Can you explain what's just south of the landing site? It looks like that might be the dune area that you've been talking about. And also in lay terms, how far are you from what you might consider to be the foothills of Mount Sharp?
John, you want to talk about the dunes?
Sure. The dunes that you see there is a rather narrow strip, and you see it slicing there through the southwest part of the landing ellipse. And so from where we think we've landed to those dunes is a matter of kilometers, a few kilometers away. The basal topography, where it really starts to steepen up there, where we would like to access it could be as much as 10 kilometers away, but as the crow flies directly towards it, it would be a much shorter distance because of that angle that you see there slicing through the landing ellipse.
Oh, then hand back the mic, please. Thank you.
So does that mean that to eventually get to the mountain, you would go north and around the dunes, or is there any reason you can't essentially go straight?
Well, we would never want to just drive across the dunes as the shortest way to go there. We have been studying them. We have this beautiful topography because of the high-rise camera and meter scale digital elevation models, and so we study those to find the paths that would give us the least resistance through it. But really what's going to happen first is the science team is going to look at the geology of the landing ellipse as a whole and then try to find a route. And if it's a more circuitous route, if the science justifies it, we will happily take that route.
Okay, we're going over on this side, right there, and we'll go to you next.
Sorry, Ian Thompson from the Register. Can you tell me what's actually happened to the lander which lowered Curiosity down? Once it released Curiosity, it pops off and flies off into another direction. Have you got any information how far away it is, what kind of condition it's in?
Go ahead.
Do I take that? Well, it flies away. It has actually a closed loop algorithm. Very rudimentary. It doesn't need to be very sophisticated because we want to crash it far away, 400 meters away. And we do tell it a heading, okay? So we told it to go essentially towards the north. Okay? And where it is, but we don't have telemetry, that part of that mission, so we don't know. So the only way that we're going to find out is through high-rise, taking an image. So, but we think it's going to be hundreds of meters. It's designed to do that.
Okay, go ahead.
Hi, Eric Han with Nature. Questions for Sarah. So you estimate that this was 6 minutes after entry, so about a minute before landing. That's after the heat shield popped off. Have you looked for that? Any sign of that in the image?
No, we haven't looked for that in this image. I don't know if we'd be able to see it in this image. I'm not sure. We will be taking images of the landing site in the days to come. We might be taking an image within the next day, but we're definitely taking, that one would be a little hazy. But we're taking a very good image 6 days from now, and then another one 12 days from now. And in those images, we'll be able to look for where the other components landed.
And as a quick follow-up, what's your best estimate for the resolution of what we're seeing here with the parachute? How many centimeters per pixel?
33 centimeters per pixel.
Thanks.
I'm going to keep handing it down the row. I think there were a couple more.
By the way, I could just add one thing on that. The image we're trying to take as soon as possible is to help with the problem that Miguel was talking about, which is to localize the lander with respect to topographic features that we can see to get it registered onto a map to aid the dynamic solution that Miguel talked about. So we hope to have that in just a couple of days.
Leo Enright with Irish Television. The blogosphere got very excited very quickly after the Hazcam pictures came down about a blotch that appeared in both of the images looking out across the plains, which they were interpreting as possibly the landing stage impact. Certainly it was, this picture came down very quickly, much quicker I think than many of us expected, and so it seemed that it could be, but I wondered, did any of you think that you saw evidence for the landing stage impact?
That artifact, whatever it is, in the image. It has been seen, it's been talked about, it's been suggested it could be something associated with landing. It could be a dust devil. I think we don't know, but we have noticed that feature, and it's too early to tell what it is, but we'd like to take a look at it again. If it's a transient feature, then we don't have another image of it. We just have that one image, right? So we can't go back and look at it. Of course, if the descent stage is there, that might tell us where to look, when we get all of our cameras up. Maybe there's some hope that, well, a Marty image might have captured something as well, the descent imager, when we get that. And we're just starting to trickle down thumbnails over the next few days of that. And it'll take a little while to get that. And Miguel, anything to add?
No.
Okay, we're going to take one more question from that row, and then Todd, we're coming over to your row next. Okay, go ahead.
Jonathan Amos, BBC News. What's the distance to the rim that we're seeing in the image here? You gave us a distance to the Mount Sharp. Give us some sense of how far we are from the large features, the topographic features that you're talking about.
Yeah, let's just pull up the image again of the, Henry, it would be the first one, just in front of this one, I believe, that's showing. There we go. So the ellipse there is 20 kilometers. So if we land just to the right of the X in the middle there, I'd guess on the order of 20 kilometers to the rim, something like that.
Okay, we'll take one here in the front row, and then we're going to move back here.
Hi, Leonard David with AIAA, Aerospace America, and Space.com. Just curious on the Sky Crane as far as residual fuel. I heard a number. I just wonder if you got refinements on it. And what was the touchdown speed? Any way you can appreciate what exactly speed you hit the surface?
Well, yes. As far as the first, I'm going to ask my friend and colleague Adam. He's not here because I don't. But yeah, it's
140 kilograms.
140 kilograms. Was it?
I think it's 140 kilograms. That's my memory. Yeah.
Yes. Okay, that sounds about right. So we ended up with a lot of kilograms of fuel, which is a good thing, I guess. That your second question,
as opposed to the opposite.
Yes. I take that first, right?
The touchdown speed.
Oh, the touchdown speed reported by the spacecraft itself, with its navigation sensor, is 0.7. It actually was dead on the money, right? Prior to it, the declaring touchdown. Okay, so we were coming at 0.75 degrees. Now that's
0.7 meters per second.
0.75 meters per second, which is the intended velocity. Now, if there is a bias or an error in the navigation sensor itself, you could not tell that. So it's going to require more analysis to really, especially for Marty, it's going to be very useful to be able to really tease out what the velocity, the true velocity is. So right now we can only give you what the spacecraft thinks its velocity was, and that was 0.75 meters per second vertically and 4 centimeters per second horizontally. Okay, so it's a very small number compared to previous attempts. So we'll see whether the imaging coming down, whether we can corroborate that number. It would be nice for a guidance and control point of view, if that's the case.
That's called straight down.
Yes.
And maybe for Sarah, just maybe gauging the difficulty, the degree of difficulty. Everybody's into the Olympics. Between Phoenix and imaging Curiosity coming in, was it tougher?
It was tougher because of the relative positions of the two spacecraft. The team sort of internally guesstimated that Phoenix they had an 80% probability of getting that image, and MSL it was a 60% probability. So this was a great shot.
Okay, Todd, go ahead.
Todd Halverson, Florida Today and USA Today, for whoever can handle it. Based on what you know right now, could you update us on when you expect the delivery of higher resolution black and white photos, color imagery, the first panorama? You mentioned thumbnails were coming down from Marty, and maybe the first full video from the descent camera. Thanks.
Yeah, so basically the date, we're still on the nominal plan exactly. And I think in one of the earlier press conferences, Richard Cook gave an approximate list of dates. So basically we start to get, we believe we'll get a front HAZCAM that has the same resolution as the rear that we were showing today in just a couple of hours from now, about 11:30. And we will start to trickle down some thumbnails from the descent imager. And then in the next day or two after that, we start getting better resolution Martys as well as our first panoramas these are black and white panoramas. We also get a single color frame from the Molly instrument, which is in the stowed position, but it looks out to the side and it can focus at infinity, and that will look a lot like a single frame, kind of panoramic image that you're used to seeing. It looks like it doesn't look like it's taken from a microscope. It looks like a regular camera since it focuses at infinity. So that will be the first color image that we get down, that Molly image, and it's about 2 days from now.
Okay, you were next, and then we're going to come forward to you, and then.
Hi, this is Mike Wall from Space.com. I guess this is for John. If you guys can't actually find where the sky crane came down, or actually identify some of the craters that were created by the ballast being ejected, I mean, how high a priority would it be to go check out those new, fresh impact craters as sort of compared to all the other work that you would like to do?
An inevitable question. In terms of where the sky crane came down the descent stage with all the hydrazine that might be present there, we would actually really prefer to avoid that. And I don't doubt that if our path of science takes us near it, we're really going to try to image it and do everything we can to study it. But otherwise, we try to avoid it. As far as the ballast goes, that was something that I was really hoping for. And then I talked to Miguel and Adam. Those blocks are ejected so far down track, we have no hope. But, striking the surface, they might give us a nice fresh exposure without any contamination. But that doesn't seem like it's in the cards.
So I'd like to add a little thing to that. We actually, on purpose, we instruct the descent stage to fly away from where the science is, so not to contaminate it. So we actually, we gave a command to the spacecraft that if you draw a line from east-west to go north of that line, exactly in what direction depends on the orientation of the descent stage at that point, because we want to do a turn with the thrusters away from the spacecraft. So we have done everything possible to fly it away from where the science is. So we would make that even more difficult to go out of our way.
Irene Klotz with Reuters and Discovery News. Two quick housekeeping questions. The first is, how many pictures, not including the stunning MRO shot, has MSL returned so far, and what time is the high gain supposed to be deployed? And then I have a question for John.
It has returned 4 thumbnails, 2 downsampled images with the covers on, and those are 256 by 256, and 1 512 by 512 downsampled rear HAZCAM with the cover off. I think that's everything.
And the high gain deploy?
High gain deploy is in the afternoon Mars time today, so about 12 hours from now or so.
Thanks. And for John, you mentioned that one of the first things you might like to do is do a representative soil analysis. I was just curious, what sort of variations in the soil is there from Viking 1 to Spirit, Opportunity, and Phoenix, if that's a valid sample? Just what sort of variation have you seen in the past, and what might you be looking for that's different on this site? Thanks.
Yeah, it's there's 2 separate objectives. The one that we're also after is the composition of the bedrock, but we infer that the composition of the bedrock is going to represent local processes that happen that form that bedrock. Whereas the soil of Mars in a place like we've landed in will represent a more global integrated average of dust that has blown around the planet and other materials that have worked their way over long distances. And while we have no independent way to demonstrate that what we might measure with Curiosity must be analogous to what was measured with Viking many decades ago, the character of the soil, every time we've sampled it, beginning with Viking and most recently with the MERS, for example, has a very high sulfur content. We'd like to know definitively what minerals are in that soil. And so by analyzing it with SAM and ChemMin, for example, we can get a better understanding of what the composition of the soil is, certainly where we've landed, and by inference maybe also globally, and through that get at one of the most global questions we could address.
Okay, we're going first to Bill Harwood and then Alan. Thank you.
Thanks. Bill Harwood, CBS News. Just continuing on soil for a minute, John, just from a mechanical standpoint, were you guys surprised at the amount of dust on the dust cover given how high the engines were, 7.5 meters or whatever, at the top of that bridle? Does that tell you anything about the consistency or the mechanical properties of the soil?
It's a good question. I think we were surprised because the images that have the dust covers off still show some dust on them. So some little bit got in there. On the other hand, based on MER experience, the dust comes and goes. And when the wind blows and it's a clear air flow, it will probably just blow it right off. And then it will come back on again when we have a dust storm or a dust devil go by. And it'll sort of wax and wane. The other interesting observation is if you look at that rear HazCam image again, you'll notice that the wheel is on relatively firm ground. And so with Miguel's estimate of 0.75 meters per second descent velocity straight down, we didn't get any sinkage there. So, you know, that's sort of an inferential science observation that the material we landed on has pretty substantial bearing strength and is probably firm. And so for that reason, we might choose to drive somewhere else to actually get our scoop out and dig in there, because the first thing that we want to scoop, we really do want to be a pretty soft material.
Thanks. And for Mike, you mentioned the health of the vehicle as you know it today, realizing it's not all in yet, but are there any glitches? Are there any anomalies at all in the data, even if they're minor? And for all of you, really, or for any of you, I mean, you guys have convinced us, you know, really how technically difficult this was. I think a lot of folks had a lot of trepidation going into this, folks on the outside. Did you guys ever imagine you'd be here this morning with the vehicle in the shape it's in, telling us this story? Thanks.
There are no anomalies that are outside the expected range that we would think is okay to proceed with activities. You know, some things are doing a little better. Some systems are, you know, reading a little higher than we expected and some a little lower, but everything's sort of within the accepted bounds that we view as being acceptable to, you know, to move forward. There's no real anomaly in work that's causing us to slow down and defer activities because of that. But, you know, because we're engineers and because we're perfectionists, every little thing that's different has, you know, folks want to go take a look at, you know, why is this 5% different from the way it was in a test, you know, and that will continue, but, you know, we're still moving forward. You know, in terms of success, I think each of us would answer that differently. I think we all believed it would land successfully, although we were worried because we wouldn't be working on it and we wouldn't have designed a 2-year surface mission with all of the science payload and a 20-kilometer traverse if we thought it was not going to land successfully. I think, as Pete Teisinger has mentioned several times, it's a very complex vehicle, and we're a little bit concerned that we would land in a safe mode or something like that, and that it would take us a little while to get out of it. We might not get a comm pass, you know, just for telecom reasons. The rover might have been perfectly healthy, but you didn't get the communications pass with the orbiter, and so you have to sit and worry and just wait. The fact that it went straight into surface nominal, didn't safe. We got great telecom performance. The orbiters performed beautifully. You know, this very complicated avionics with, you know, redundant computers and redundant avionics modules has all been fine. And I think we're pleasantly surprised at how smooth that part is going. And Miguel, do you want to comment on the EDL?
Yeah, you explained it very well. I mean, if we didn't feel that it was doable, or we felt there was no chance of success, we would not be doing it. That said, I mean, we train ourselves for 8 years to think the worst all the time. How can we, you know, if you're in the shower thinking, what thing can give you a bad day? I mean, that's what you do. I mean, it's constantly thinking ways that things can go wrong so you can go and do something about it. and then you can never turn that off, okay? And then it's all the way in, you are, and especially the few days into the the few days coming to the landing, when you also know that you don't have time to recover, it's even more, the pressure is even higher. It is a landing is a little bit like a rocket launch, okay? It's that type of violence that's so unforgiving, okay? And even till this day, once in a while we lose a launch. And we were very nervous on this launch. And those are things that we practice much more. You can actually count the numbers of Mars landing with one hand. And so it's going to take a long, long time for us to really be totally sure that these things are going to work like you feel sure about an airplane taking off and landing. So, but that's what we're going to we're going to continue trying, and we're going to be nervous the next time the same, no matter how well this one worked.
I think we need two hands now, though. I think we reached a state where we
can't count anymore.
Just barely. Just barely.
I'm not doing too badly.
Alan Boyle with NBC News, and just a couple of questions that I may have missed. Is there any Marty imagery from the descendant imager? And on the MRO picture, what's the distance from which that picture was taken? Where is the rover in relation to MRO?
There is no Marty data down right now. In about an hour and a half from now or so, 2 hours, we're going to get another pass from the orbiters, and we might get some Marty thumbnails in that. These are very small to help us understand what are the right images to to grab from Marty. But as of today, they're not down.
And MRO was 340 kilometers from MSL.
And I'll just point out that we do hope to hold another news conference at 4 o'clock today Pacific time to show the Marty thumbnails if we do indeed get those today. So we'll have an update for you that soon. All right, let's go back to...
By the way, I want to correct one thing I said about the time of the HEA deploy. I think I said it ends in the afternoon about 1 o'clock. It starts about 11 o'clock, Mars time. It ends in the afternoon. It starts just before noon.
Okay, let's go first to Emily Lakdawala, and then we'll go back to John Johnson. She's got her hand up. There we go.
I have two questions. The first one is, do we have any information yet on the health of any of the science instruments?
Yes, we have health of many of them, all of them that we've done a checkout, and they're all fine. They're all in perfect health and operating as expected.
And the second one is that it's a well-known adage that if you get 406 scientists in a room, there will be 407 different opinions about what's going on. So I was wondering, I know it's very early, but if you have any kind of different ideas that are floating around about some of the things you're seeing in the foreground there.
It is, I think it is still early, and as you might guess, there's only a limited amount of information that we can draw from this, and I think that the team, we had a great discussion this morning, and I think most people felt that we're on a gravel plain of Mars, a somewhat familiar scene, but with a rather uniform grain size distribution. This does not look like a ballistic impact ejecta, for example. And is that the rim in the background? Everybody agrees on that. We had a lot of discussion about the alluvial fan, how we might explore the ellipse, and discussion about that. I'm kind of amazed with, we did this crowdsourcing exercise and mapping, and a bunch of people got quads, and we had a remarkable amount of agreement, which is probably mostly a testimony to the relative simplicity of the geology. And that's a good thing, because we're a complex spacecraft, and simple geology is a good thing to start off with.
Okay, I know we've had, you've been waiting for, oh, I'm sorry, John Johnson is next, but after that we're going to you, and then we will go back down that row over there and then come back here. Thanks. Go ahead, John.
Thank you. I just wanted to follow up on the last question about the health of the science instruments. It seems to me the SAM instrument with all those moving parts is particularly, well, I don't know if delicate's the right word, but you say the instruments have so far checked out. I mean, can you say anything specifically about SAM and whether you feel confident everything is in shape?
John, you want to comment on that?
Yeah, there's a series of tests that relate to SAM's performance, and so today it was an electrical test that worked well. The first test and everything looked nominal with regard to that.
Okay. And what happened to that dust storm that was talked about a couple of days ago?
Dissipated.
Oh.
Beautiful clear day.
Okay.
When we landed, yeah.
And certainly you're right. You know, we have not completely checked out all the modes of these instruments. We first do kind of just electrical test and basic test of the instruments. And there's a lot of scientific calibration and a lot of extra modes and complex modes of the instruments that will take us a long time to get through. And that's true of our own systems. You know, the drilling system, the saw spot, all of that. So we should not think that we're completely out of the water yet. We've got weeks, if not months, of checkout before we're completely confident in the entire payload.
Yeah, just to add a little bit more, the one major observation that we planned today is a rad observation for 5 hours. And there was plenty of time to do that. So that's not a checkout, that's 100% data collection.
Hi, I'm Rafael Garcia with Folha de São Paulo, Brazil. My question is for Sarah. Will MRO be able to spot the rover in the ground, even if it's just a single pixel? And will the arbiter have any role in helping the rover navigate apart from relaying the data?
Well, first, yes, we're going to be able to see the rover. We've already got images planned for later this week to look at the rover, and they should look great. You know, it's going to be more than just a single pixel, and we've already done a lot of data collection for the rover. We've mapped out, we've collected data across the entire Gale crater and the landing ellipse, and we've got stereo data and color imagery that have already been used to start looking at potential traverses. And as the mission goes on, we are expecting MSL to come to us and say, oh, we need a new picture there to make sure that there's no new dust hazards, or, it's a spot that, maybe you want a slightly better resolution at that location. So yes, we're, in addition to relaying the data, the cameras are expecting to help out.
Yeah, and I would reiterate that the MRO data that we have has been absolutely critical to landing site selection. Our ability to find safe, flat spots with relatively few rocks. As mentioned, we basically tiled all the landing sites with the potential landing ellipses with 1 meter type coverage, even stereo coverage. And our rover drivers have actually started to use those maps to plan out long-term traverses, good candidate traverses. And I think there was an earlier question about driving across dunes versus other terrain. And the rover drivers actually have algorithms that say, it's slow to go over dunes, or it's dangerous, and it's fast to go over, non-sandy surfaces, flat surfaces. And so they've tried to present some optimal options, optimal paths to the science team to take a look at, and they'll be working closely with the science team and with John to come up with those drives, and they're up until now basically 100% based on high-rise imagery.
Frank O'Brien, Americaspace.com. So now you have 2 working rovers on Mars, and one of them has a tremendous amount of data that you're going to be expecting every day. Are you going to be getting into situations where you're going to have scheduling constraints on the orbiter relays or the DSN?
No, actually, the orbiters are able to support both. In fact, Odyssey has 2 partitions that can cover the largest paths that either MER or MSL can generate, and so we think there's very little conflict there.
I just want to add, there are also the 2 rovers are in different places, in such different places that the timing of doing one relay, it's not going to interfere with the other.
Okay, Leo's going to go next, and he will run that mic down your aisle there. Okay, Leo, go ahead.
So, Leo Enright from Irish TV again. I'm sorry if I have to ask Mike Watkins to clarify his clarification about the HGA deploy. You said 9 o'clock. It's just I can't do it in my head, the translation. You said 9 o'clock local time for the deploy, but you're now saying something different. I wonder what that was.
No, I said afternoon before, and it actually ends in the early afternoon rather than starts in the afternoon. So it starts around 11 o'clock Mars time, and right now it is about 12 hours after landing, so it's about 3 o'clock in the morning on Mars right now.
So 8 hours from now.
8 or 9 hours from now, yeah.
Okay, and if I may, just a quick question for John Grotzinger. Some light reading, perhaps, since we now are going to get to know this crater very well. Can you recommend a paper that would kind of be the definitive one to read while we eat our cornflakes?
Yeah, I'm a little bleary and can't just recite the references right now, but there are several review papers that have been written, and if anybody sends me an email, I'll be happy to send those along.
Jonathan Amos, BBC again. You know the orientation of the rover now, so you know the orientation of the Mali camera. What is going to be in that first color image?
I actually do not know that. That's a good question. I should know the answer to that. We can quickly tell you that. But after
It's stowed and looking out to the side.
Yeah.
And so we had always hoped that the rover might land with an orientation where Mali might actually capture Mount Sharp, and it's potential that it would be either oblique or toward the crater rim.
I think it's going to be on the flanks of Mount Sharp and Crater Rim. But it matters a little bit. You know, we have this 112 degree azimuth plus or minus 5 degrees or so. It matters kind of exactly where how the flanks are and where the central peak is. And I think we probably could get a better answer for you relatively quickly.
You'll see it tomorrow at this time at the press conference.
Hi, yeah, Eric Ham with Nature again. So let's assume that Miguel's tracking data for the moment is correct and that you've landed 2 kilometers or so down track, a little bit closer to Mount Sharp than you expected. So John, my question is for you. Behind you, you have where you thought you were going to land, you know, the foot of the alluvial fan with those interesting thermal properties, and in front of you is your main target. So are you going to go in reverse, or are you going to go ahead?
Well, you know, the boundary between where the alluvial fan ends and the base of Mount Sharp is diffuse. All alluvial fans ultimately taper out and they fine in grain size. And we really want to be on the downslope side of that if that's what's going on there. So the goal of the crowdsourcing mapping exercise was to be able to compile a map that made a first crack at sort of units, different types of geological units, but also IDing key bits of outcrop, maybe the height of the podium here. 1 meter, 2 meters, maybe 3 meters, things that constituted part of that 1% EDL risk. That's what we're after. And so what we would do is string together a pathway that would link us between these, and if it takes us back towards the fan, then we'll go that way. And if it takes us forward, then we'll go that way too. So, you know, most geological mapping exercises do not involve a traverse in just one straight direction, and our goal is not just to head for the hills.
What are the size of these boulders that you want to string together?
Well, you know, each one of these quadrangles is roughly about 1.5 kilometers on a side, and within every one of them, there is some kind of a scarp. And so what we're trying to do is to piece together a stratigraphic section of the landing ellipse using the mapping as an efficient way to go around and check all of the points that would contribute towards that stratigraphy. And probably speaking.
You said you were trying to string together certain objects
Yeah.
in your path. What are those objects?
We don't know yet. Stay tuned. Yeah.
Guy Norris from Aviation Week. I'm not sure who exactly can handle this best, but under the nominal commissioning schedule that you do have at the moment, when could we expect the first motion for the vehicle to be commanded? And secondly, really, is the vehicle at the moment, the rover, is it configured essentially how the model is right now with the center set of wheels in that stowed position? Thanks.
So it is, no, it's actually sitting flat right now. So it's, you know, here it's up on a podium. It's actually sitting quite, you know, it's sitting quite flat like this now, with the RSM down and the HA about to come out. So it's sitting, I can't lift it up without the system changing, but it's, I'm going to do it this way. Right, it's sitting quite flat now as far as we can tell, within, you know, a couple of degrees, right? And what was the other question? First drive. I would say a couple of weeks is a good number for that. And it will be quite a short drive, you know, 1 meter or 2 or something.
scientist. I had a question for Sarah and then one for everyone here. Will HiRISE be able to see the craters that the ballast made, and do you plan to look for them?
I'm not sure. We are going to be looking for the various hardware components in future images, and I don't know what we're going to see.
And then for all of you, I heard you're going to be living on Mars time for the first 90 sols, is that right? And how come only for 90 sols, and then what happens after that?
Well, that's a good question. That's a good question. And I'll answer that. I was joking with Gentry just before this that you can tell who was working on a Mars time here at night by who's still wearing the landing shirt. John. The thing about these missions are really twofold. One is we have to learn how to use this very complicated machine that we've built. And it's in a new environment, and it behaves differently than it did in the test bed here. It's got different gravity, it's got different temperatures, it's got everything. Different from exactly the way we tested it. And we tested a range of activities, but you have to find out exactly how it's going to behave when you're at Mars. And we need to get comfortable with that. We need to do that efficiently. So we want to run through our paces in an efficient way. And by working Mars time, it gives us basically 16 hours to plan an uplink while the rover is sleeping at night on Mars. So we can take a long time. And of course, if we don't rotate with the Mars day and night, then we start to lose time. We start to lose that ability to keep track of the Mars night while we're working. Now, that is to help us be efficient in checking out the vehicle. But there's another complex thing that we have to learn, and that's how to operate with ourselves. We have 420 people or something, I forget the number, John, on the...
Just the scientists.
Yeah, 400 scientists on the mission, and another 300 or more engineers on the mission. So we have something like 700 or 800 people learning to operate this vehicle. And we have to know how to interact with ourselves. We have to know each other's voices. We have to know how each other operates. And we have to learn each other's individual specialized skills so that we can get more efficient in the future. So after this 90-day period, we get to know each other very well. Then we can send folks back to their home institution and go back to France and go back to Spain and go back to Goddard and go back to places like that, work a more normal time, operate by the internet, operate by telecom, and we know those people, and they know us, and they know the rover, they know the software systems, and we'll be much more efficient. So this is really kind of a immersion training, like a foreign language, right? Where we were learning both how to operate the vehicle and how to interact with each other.
Let me just add one more thing to that. As if it wasn't challenging enough to work on Mars time, on MER, at the end of the sol, we have a X-band link to Earth to send all the critical data back, and that could be scheduled exactly on time. On this mission, because of the larger data volume, we need to grab an MRO or an Odyssey pass. And so the way to think about it is a Mars time rotation of 39 minutes every day, but now add plus or minus an hour and a half to randomize your schedule just to make sure that anybody you wanted to have a relationship here on Earth could get really screwed up.
It's also great the way we're starting. People talk about it being like jet lag. And it is like jet lag in a certain sense. We're off by 12 hours now, except that it's also daylight when you're trying to sleep. So at least when you fly to another country and you have jet lag, it's nighttime and you're trying to go to sleep at night. And here we're exactly out of sync. So we're starting off in kind of the worst time, but it should actually get a little easier here over the next few weeks.
Okay, Henry Bortman has a microphone, and then I know there are a few questions coming forward again. So go ahead, Henry.
Question, Henry Bortman, Astrobiology Magazine. Quick question about the Martian calendar. Does Sol 0 start at touchdown or at local midnight at the landing site?
Local midnight.
Someone else on this end, Todd, and then we'll just keep moving forward.
Todd Halverson of Florida Today and USA Today. I might have missed this, but could you tell us what configuration the vehicle is in the picture behind you? Is the heat shield still on there, and is that what the white albedo is there? And I was also wondering if you could address the historic nature of what went on last night and how you think this will be viewed 10 years from now, 20 years from now, 50 years from now? Thanks.
I see my EDL colleagues around to be able to tell me what is the heat. Is it before the heat shield or is after the heat shield deploy?
I don't think we know for sure yet.
We don't know for sure yet.
We don't see it.
Yeah. But by time, I mean, we need to do the reconstruction.
I think the white thing, Steve,
that is the back shell.
That's the back shell.
That
right?
is the back shell.
You're looking at the top of the
Yes,
back shell, right? The
yeah.
heat shield would be underneath, so it's not easy to see in these
you will not-
images
you
whether
will not
it's
see
off
it.
or not. So we'd only know by timing, and we don't know that yet.
And from a philosophical point of view, I mean, the fact that we see ourselves arriving to another planet, just like Phoenix did first, I mean, it's just mind-boggling to me, I think, to all of us. So, I mean, I cannot say more than that. It's just the coolest thing.
Okay, move forward one more here.
Kelly PD Sky and Telescope. I was outside for a bit, so I apologize if this has been asked. 140 kilograms of hydrazine, is that a concern? Did you have the flyaway be in the downwind, prevailing wind direction? Can you talk to that a bit?
Well, I could not tell you about the wind. I mean, it was the choice to fly it as far as possible. Well, the direction is we have limited control, okay? So you draw a line east-west and fly north of that line, depending on what orientation the descent stage it finds itself. The reason for that is that we do a tilt maneuver, and the thrusters are canted. So we do it about an axis that would not plume the rover. So if the thrusters are, here, we don't do the turn maneuver this way. We make it this way. Okay, so that means that we have only two choices: either go that way or that way. And so we choose the one that goes north. Okay, so when we do our simulations, you'll see a whole bunch of dots on the northern hemisphere of the two north quadrants. So that's what we do. Now that was picked up between the scientists and the engineers looking for all the conditions, including winds.
Okay, let's go to Irene again. Oh, I'm sorry. Irene, take the mic, but we have a question back here first that we'll take.
Thank you. Jackie Goddard for the Times of London. I just wanted to clarify first with Sarah, when you say 340 kilometres away that image was taken, is that direct vertical altitude? And then my second question, just for Mike Watkins, to the untrained eye, these are pictures of black and white pictures of gravel. To the trained eye, can you sum up just how sophisticated and exciting and momentous these pictures really are?
Okay, it's the 340 kilometers is line of sight, so it's not. I think, yeah, we were almost directly overhead. I think we had a very, very small angle. It was essentially overhead.
I'll take a crack at the photos, and I'll let John take a better crack from the scientific perspective. To me, it's representative of course, a successful landing on Mars. It's representative of a new home for the rover. It's representative of a new Mars that we have never seen before. And so every one of those pictures is the most beautiful picture I have ever seen. I think John would say this, that if those pieces of gravel are transported by water on Mars, an ancient Mars, then they're much more than gravel. But John, you should pick up from there.
Thanks for setting me up, Nick. A minute ago there was a question down here about what this mission means to you, and I think for us at this point as scientists, we haven't even scratched the surface, and really what's amazing about it is the miracle of this engineering. That's all you can do is sit there as a member of the science team, and Don Hassler's a PI of the RAD instrument. He's sitting behind you there. He's nodding his head. It is a miracle to us that we have chosen this place as a result of scientific deliberation. This EL system for the first time in the history of landed missions, allowed the science community to choose between 4 options. None were excluded by engineering. The final 4 was a debate of scientists that like different flavors of chocolate and vanilla. And then when it comes down to creating a priority of images to downlink, and you have your choice of the front has-cam and the rear has-cam, the most amazing thing about it, to get back to one of the things that Emily was pointing at, you have a group of engineers and a group of scientists, and here's what happened. Jennifer Trosper comes up to me and says, John, we really need to get the engineering state of health data down. That's a top priority. And I said, of course, I agree. And we think we might be able to sneak in an image. What would be your first choice? Would it be the front has-cam or the rear has-cam? And all of the scientists wanted the rear has-cam. And all the engineers wanted the front has-cam. And the reason for that is they said, well, there's no obstructions in the way. The wheels aren't in the way. It's the most open view of the terrain. Isn't that what you would want? And all the scientists said, no, we want to see the wheel on the ground because this is not a moment for science. It's a moment for engineering. And when you see that wheel on the ground, you know you've landed on Mars. No semaphore tones, no people jumping up and down. You actually see a picture of the surface of the planet with a spacecraft on it. And that is the miracle of engineering.
Thoughts with Reuters. I'm not sure who to ask this to, and please don't laugh if it's really silly, but with the nuclear power source, could you just explain a little bit about why daytime and nighttime and rover sleep is important or a factor?
Sure, and it's maybe not quite as obvious as it's certainly not a silly question at all. So the RTG generates just a little bit of electricity. And we think of it as a trickle charger of our batteries. And we are always operating on the batteries during the day, and at night we're trickle charging them back. The other big advantage is it generates a lot of heat. Most of what the RTG generates is heat. We take a little bit of that heat with a thermocouple and make a little bit of electricity, 100 watts or so. But that heat keeps us warm. It prevents us from having to use a lot of heaters, electrical heaters, for warmth. So we circulate fluid, a fluid loop. You think of it like a Freon loop or something in an air conditioner, to take that heat and pump it around the rover body and keep the rover warm. So we still need that. That's where most of the energy goes, and the rest of it trickle charges our batteries, and we use the batteries during the day. And that's not as big limitation as you think, because of course we want to take pictures and we want to see what we're doing, and we want to look at the workspace and look at rocks and pick targets out, and you want to do those things during the day and not at night. It's warmer during the day, so it really fits pretty naturally the operations concept that you'd want to do.
All right, we're going to end the press briefing for today. Of course, those of you in the room can come up and ask some more questions afterwards. As a reminder, I already mentioned 4 o'clock today. We hope to do that follow-up news conference with Marty Images. After today, we will do daily 10 a.m. news conferences, so please join us for those. And if you want to stay in your seats, we're going to take one look again at what it was like in Mission Control last night at 10:30. Thank you for joining us.
Things are looking good. Coming up on entry. Vehicle reports entry interface. We are beginning to feel the atmosphere as we go in here. It is reporting that we are seeing G's on the order of 11 to 12 Earth G's. Reversal 2 is starting. We are now getting telemetry from Odyssey. We should have parachute deploy around Mach 1.7. The parachute is deployed. We are decelerating. Speed chill has separated where we found the ground. We're down to 90 meters per second at an altitude of 6.5 kilometers descending. Standing by for batch shell separation. We are in powered flight. We're at altitude of 1 kilometer descending. Standing by for sky crane. Sky crane has started.
signal to us. You remain strong.
Touchdown confirmed. We're safe on Mars.
Got thumbnails.